Greetings, students. Today, we delve into an intriguing challenge from the world of algorithmic problem solving, specifically LeetCode Problem 347. This problem invites us to explore the realm of frequency analysis within an array of integers. Our task is to identify the top k most frequent elements within a given array. To clarify, we are provided with an array of integers and a value k, which signifies how many of the most frequently occurring elements we must extract. For example, consider the input array 1, 1, 2, 2, 3 with k equal to 2. Here, the number 1 appears 3 times, the number 2 appears twice, and the number 3 only once. Thus, the two most frequent elements are 1 and 2, leading us to the output 1, 2. As we embark on this exploration, let us consider the implications and strategies for efficiently determining these frequent elements. The concept of a frequency array with a list is essential for understanding how we can efficiently count and organize elements in a collection. Imagine you have a basket of fruits, and you want to know how many of each type you have, while also remembering the order in which you picked them. In this structure, the frequency array acts like a tally sheet, where each fruit corresponds to a specific index, counting how many times each fruit appears. Meanwhile, the list keeps track of the unique fruits in the order they were first picked. For instance, if you picked an apple, a banana, and then another apple, the frequency array would show that apples appear twice, while the list would show apple and banana in the order you encountered them. This dual structure is powerful in various applications, such as analyzing text data or creating histograms, where you need both the count and the order of elements. By iterating through your collection, you can populate the frequency array and the list simultaneously. When you see an element for the first time, you add it to the list and set its count to 1. If it appears again, you simply increase its count. This method optimizes both space and time, allowing for quick access to the counts and the order of elements, making data analysis not only straightforward but also efficient. In this slide, we're looking at a function called frequency array, which helps us count how many times each item appears in a list. First, we create a dictionary named frequency. Think of this dictionary as a tally sheet where we'll record each item's occurrences. Next, we loop through each element in the input list, which in this case contains fruits. For every fruit, we check if it's already in our dictionary. If it is, we increase its count by 1. If it's not, we start counting from 0 and add 1. This is done using the get method, which safely retrieves the current count or defaults to 0 if the item isn't found. Finally, the function returns this frequency dictionary, which tells us how many times each fruit appears in the list. For example, when we call frequency array with our list of fruits, it will return a dictionary showing that apple appears twice and banana appears 3 times. This helps us see which items are most common, which is especially useful in many data analysis tasks. A priority queue is a unique data structure that organizes elements based on their priority rather than their order of arrival. Think of it like a hospital emergency room, where patients are treated based on the severity of their conditions instead of when they arrived. This means when we need to find the top k elements, which have the highest priority, we can do it quickly and efficiently. The real power of priority queues comes from their ability to handle changing data, making them ideal for tasks like scheduling or managing resources in networks. Typically, a priority queue is implemented using a binary heap, which allows us to insert and remove elements efficiently. When focusing on the top k elements, we can utilize a min heap, keeping track of the smallest element among the top k. If a new element comes in that is larger than this smallest element, we replace it. This dynamic approach ensures we always maintain access to our top k elements, optimizing performance as our data scales. In this example, we're implementing a solution to find the top k frequent elements in a list using a priority queue, specifically a min heap. First, we import the heap queue module, which provides us with the necessary functions to manipulate the heap. We start by defining our function, top k elements, which takes in a list of numbers and the integer k. Inside the function, we create an empty list called min heap, which will hold our top k elements. Next, we loop through each number in the input list. For every number, we add it to our min heap using heapq.heappush. If the size of the heap exceeds k, we remove the smallest element with heapq.heapPop. This ensures that we only keep the k largest elements in the heap. Finally, we return the contents of the min heap, which now contains our top k-frequent elements. In our example with the input list 3, 1, 5, 2, 11, and k equal to 3, the output is 5, 12, 11. This method is efficient and allows us to focus on the most significant elements easily. A hash map for element counts, also known as a frequency map, is a powerful tool in programming. Think of it like a smart tally counter. It allows us to count how many times each unique item appears in a collection, such as an array or a list. By mapping each distinct element to its count, we can quickly check how many times an item shows up without having to scan through the entire dataset repeatedly. This structure is especially useful when dealing with large amounts of data. For instance, in text analysis, we can count the occurrences of words efficiently. The beauty of a hash map lies in its speed. Both inserting new counts and looking them up typically take constant time, denoted as O1. How does this work? A hash function converts each unique element into a hash code, which serves as an index in an underlying array. When we need to update an element's count, the hash map retrieves the correct index and increments the count quickly. This not only saves space by storing just unique elements, but also simplifies counting, allowing us to handle everything in a single pass through the data. Here we have a function called countElements, which is designed to count how many times each element appears in a list. First, we initialize an empty dictionary called counts. You can think of this dictionary as a tally sheet where we'll keep track of each element we encounter. Next, we loop through each element in the input list. For each element, we check if it's already in our counts dictionary. If it is, we simply increase its count by 1. This is like adding another tick mark next to the element on our tally sheet. If the element isn't in the dictionary yet, we add it and set its count to 1, marking it as a new entry. Finally, we return the counts dictionary. For example, when we input the list of fruits, apple, orange, banana, apple, the output is apple, banana 2, orange 1. This shows that apple appears 3 times, banana 2 times, and orange once. This function is a straightforward way to gather frequency data for any list of items. To solve the problem of finding the top k frequent elements from a list, we can break it down into a series of clear steps. First, we need to count the frequencies of each element using a hash map or dictionary. This is like tallying votes in an election. For each number in our list, we update its count. The code snippet here shows how we achieve that. Next, we utilize a min heap. Think of a min heap as a priority queue that always keeps the smallest item at the top. This is crucial for efficiently retrieving the top k frequent elements. As we build the heap, we ensure it only retains the size of k. If we add more elements, we remove the least frequent one. This process is illustrated in the next code example. After constructing our heap, we extract the results. By popping elements from the min heap, we can gather our top k frequent elements. Finally, we return this list of elements. The entire process is efficient with a complexity of O n log k, where n is the number of elements, thanks to our use of the heap. This method allows us to find the most frequent elements clearly and effectively. In LeetCode problem 347, we are tasked with identifying the k most frequent elements within an integer array, nums. The result can be returned in any order, but crucially, we must achieve this with a time complexity better than O n log n. The constraints specify that the array length can be up to 100,000, with element values ranging from -10,000 to 10,000. Additionally, k is guaranteed to be within the bounds of unique elements in the array, ensuring a unique solution. The provided solution addresses LeetCode problem 347, which involves finding the top k most frequent elements in a list of integers. To tackle this, we use a combination of a hash map and a heap, ensuring efficiency and clarity. First, we create a frequency map using default dict from the collections module. This map links each unique integer in our input list, nums, to how often it appears. Think of it as counting votes for each number, and since we go through the list just once, this step runs in linear time, O n. Next, we want to identify the k integers with the highest counts. Here, we use the heapq.nLargest function, which efficiently pulls the top elements based on their frequencies. The heap helps us quickly find the largest values, similar to how a priority queue works. Overall, our algorithm runs with a time complexity of O(n) plus k log n, balancing the counting process and the heap operations. By choosing a hash map for counting and a heap for retrieval, we achieve an elegant solution that is both space and time efficient. Let's examine the time complexity of the top k frequent elements problem. The overall time complexity is O(n) log k. Here's how it works. We often use a heap, or a priority queue, to keep track of the top k elements. When we insert or remove elements from this heap, it takes O log k time. Since we need to process n elements in total, multiplying these gives us the total time complexity of O(n) log k. Now let's consider the space complexity, which is OK. This is because we only need to store the k most frequent elements in the heap. So, the additional space we use is directly proportional to k. In summary, the efficient use of a heap allows us to manage both time and space effectively, ensuring we can handle large data sets while still focusing on the most relevant information.